So I'm gonna have to move. So everybody, hopefully you can see my hand. Is that what you can see? All right, you can see my hand. All right, okay. So the first thing was somebody asked, are you gonna get cheat sheets? Well, yes and no. You get to make your own cheat sheet. I will actually, as we move through the semester, I will start telling you we're building our toolkit. And that's really what we're doing. We're building our toolkit. So as we start looking at equations, we'll go there. So everybody, not everybody, a lot of you asked me questions about this dimensional analysis. And basically, if we look at physics and chemistry, numbers have units. Numbers totally have units. So if I am dealing with length, width, height, these are in or the pre-work problem that we had tonight. You had something that was like L and W and H, and it asked you if I have volume, what are my units going to be? Well, my units are going to be, I've got length times width times height. So I have meters times meters times meters, which gives me meters cubed. So that was one of those problems that we were looking at meters. Now, sometimes W is going to mean weight, and weight is a force. And our units of SI units for force are going to be newtons. And 1 Newton is a kilogram meter per second squared. So if I'm looking at an equation that says my force is equal to mass times acceleration, and my units are now kilograms, and acceleration is in units of meters per second squared, now I've got units of kilograms, meters per second squared, and life is good. So what we're saying is this. So let's take an equation that I have x, and x means position. And I have velocity. And I have time squared. And that's time. So if I'm doing my dimensional analysis, what this is saying is that my meters, question mark, velocity, which is in meters per second, and my time squared is in seconds squared, I have meters per second, second squared. That cancels, that cancels. This side of the equations is meters per second, and this side of the equation is meters. That's not equal, and that's not dimensionally correct. So let's take a common example that people have worked with, and most people, by the time they come to general physics, have been in general chemistry, and I also teach general chemistry. So that we know density is equal to mass divided by volume. All right, so my density is mass divided by volume. Well, we've seen it happen before. Somebody gets density, writes it down, gets sloppy, and says density times mass is equal to volume, because we got sloppy on what we wrote down. We didn't write down the right equation, or we did something, a little sloppy. Well, my density units are kilograms meters cubed. My mass is kilograms, and we know my volume better be meters cubed. Uh-oh, I've set up my problem wrong. I've made an error in my problem. So unit analysis is really going to help us in our problem. So next week when we come together, we're going to look at our kinematics equations of motion. And I will start posting some lectures on kinematics because some of you are going to want to work ahead. But we know that position is equal to velocity times time. Or we can look at it this way. Velocity is defined as, and we'll use a delta meaning change. So it's my change in position with respect to time. So my units are in meters per second. But if I'm doing position, velocity, time here, all right, position, velocity, time, I'm going to be in meters is equal to meters per second times seconds. My seconds cancel out. I've got meters, and I know I've set up my equation correctly. Now, acceleration is going to be a change in velocity with respect to time. So this is going to be in meters per second over seconds, and mathematically we can write that out as meters per second squared. But I can use A for acceleration, and I have velocity divided by time. And so now if I do a velocity time plot, check that out. My slope of a velocity time plot, so if I have velocity and time and I have a straight line, that slope is equal to, if I do rise over run, this is a change in velocity over a change in time, and that slope is going to be an acceleration. So for those 4 graphs that you're looking for an acceleration, if I do a velocity versus time plot and I get a straight line, remember that's y is equal to mx plus b, where that's the slope. This is our equation of a line. And if I rewrite this in terms of my units that I have, guess what happens? I have position, I have my slope, I have time, and now we know that slope is an acceleration, and I can read that acceleration right off of my graph. I can read that right off of my graph. Now, some of you are going to say, I need to memorize that equation. Well, just like what you've done before, the more you use something, because how many of you can say that sodium, you know, the elemental symbol for sodium is Na. We've done it, we've used it, you're going to use it. All my tests are open resource tests. So memorization isn't necessarily going to be something that you have to worry about. You're going to learn it because you've used it over and over and over again. But all my tests are open resource. It's too hard to try to police that. Okay? Too hard to try to police that. So let's go back. Let's look at another. We're going to find in our toolkit, we're going to get 3 equations for kinematics in our toolkit. One is a change in position is equal to initial velocity, and that usually means initial, times time plus 1/2 acceleration times time squared. We will use my final velocity is equal to my initial velocity plus an acceleration times time. And we will use that the final velocity squared is equal to my initial velocity squared plus 2 times my acceleration times my change in position. And these are our 3 kinematic equations. And we'll go more into that next week. but I want to do this from a unit analysis point of view right now. And this is the one that'll set you up for the lab that we're doing. So let's look at this one. My velocity, so we'll do number 1 here. I have meters is equal to meters per second times seconds plus 1/2 meters per second squared times seconds squared. I'm going to end up seconds cancel, second squares cancel. I end up meters plus 1/2 meters, but I get those units I can add together and I'm dimensionally correct. So if I do a position versus time plot and I get a curve, and what we saw when I did that one, I showed you that y was equal to 0.6782x squared plus 0.0075x plus 0.002. This will be position is, well, my y is position. And now I've got 0.06782 t squared plus 0.0057 t. Let's look at my first equation. I have position. I have 1/2 acceleration times time squared. And I have initial velocity times time. Well, there's my initial velocity. And that's 1/2 my acceleration. I can read it right off of my graph because this is modeling that particular equation. And it's modeling that particular equation. So if I look at my second one, that's meters per second is equal to meters per second. And now I've got meters per second squared times seconds. That ends up in meters per second. And I can add those together. This one gives me meters squared seconds squared is equal to meters squared seconds squared plus 2 meters per second squared times meters. That gives me meters per second squared. So the dimensional analysis is really, really going to help you. All right, we want to do a trig review, real quick trig review. So I have a right triangle. Now, if you look in your book, they're going to give this an R, they're going to give this an X, and they're going to give that a Y. And if you remember that, and this is going to be the angle that I'm working with, and if you remember that sine of the angle is going to be Y over R, cosine of the angle is going to be X over R, and tangent of the angle is Y over X. That's all well and good and great. Except in physics, we do weird things. Okay? For example, we're going to take a block on a plane. My gravity is going to act on my triangle like this. I'm going to draw something that we're going to call a normal, all right? And this angle here is equal to this angle there, and life isn't necessarily fun. This is going to run parallel to my table, and this is going to run perpendicular to my table. And if I played with X and Y's, my picture doesn't work. And you're going, oh God, how do I switch around? So I like to do it this way. This is my adjacent, this is my opposite, and this is my hypotenuse. And this now gives us, this is my opposite side over my adjacent side. or no, over my hypotenuse. Sorry, I was getting ahead of myself. This is my adjacent side over my hypotenuse. And this is my opposite over my adjacent. And if I remember that, it's going to make my angles work a lot better. It's going to make it a little easier. Then I can I can have my triangle any which way. And as long as I know what angle I'm dealing with, life is much better. So it's a nice way to remember it. We also know Pythagorean's theorem, a squared plus b squared is equal to c squared. Well, this gives me my x squared plus y squared is equal to r squared. And we're going to use this over and over again. But why is this important? Well, one of your homework problems is I want to find out the height of the building. And I know how far away from the building I am. And I can measure this angle a variety of ways. I can use a protractor, I can use my phone, I can do this. And if we know that side, the height, right? So if I'm doing this, I know that the tangent of the angle is going to equal the opposite, which is the height that I'm looking for, divided by the distance away. And now I can do distance away times the tangent of the angle is going to equal the height of my building. So the key is knowing what angle you're working with. The key is knowing what your right angle is. And then we're going to use this over and over and over again throughout the semester. But this is as much trig, but we'll do a couple of other things with trig, but this will get you the majority of what you need in order to work problems this semester. And I'm guessing brains are full.
Could you go back to the last page that you were working on real quick?
That one?
Yes, thank you.